Okay, good morning, everyone. Welcome to today's seminar. I'm pleased to introduce Gabriele Bruni, a colleague of ours that has been working as a researcher at our institute for a few years. Gabriele got his degree at the University of Turin in 2008 with a thesis on the first data collected by Argo experiment in the TV band. Then moved to Bologna for the PhD, where joined a multi-wavelength project working on the connection between winds and jets in BAL quasars. In 2012, he moved as a postdoc researcher to Spain in Granada and to Germany at the Max Planck Institute of Radio Astronomy in Bonn. In 2017, he started working with the integral groups here at IAPS, where he takes care of the radio counterpart of high energy sources, including AGN and transients. Before giving the floor to Gabriele, I would like to remind you that we will have the opportunity to ask questions and make comments at the end of the talk. Those joining remotely can write their questions or comments in the chat or raise their hands to ask them directly to our speaker. So I give the floor to Gabriele for his talk, Unveiling the Mystery of Fast Radio Bars Through the Environment.
Okay, thank you, Giovanni. Good morning, everyone. Today I have the pleasure to show you the results we got on the fast radio bars in the last couple of years. This is a very vibrant field, and everything needs to be discovered. So I will show you what we understood until now and what we can do in the future. The collaboration is broad and includes people both here in Rome, in IAPS, and at the Observatory of Bologna, University of Calabria, plus abroad. And we are trying to cover different bands for fast radio bars, so not only radio, but also optical and up to high energy to characterize the host and the bars itself. So let's start from the beginning. Fast radio bars are the newcomers of transients world. The first one was discovered just for serendipitous discovery, and it was 2007 when Duncan Lorimer was analyzing some archival data. He's a pulsar scientist, so he was analyzing Parkes telescope archival data to look for bars, and he found something very strange. It was a very strong pulse with affluence much higher than what you expect from pulsars, and a short, even shorter than some of the pulsar bars. So the first indication that this was far away was the dispersion measure that was 10 times larger than the galactic one. So he supposed this was an extragalactic transient, but still this was the first case, and also for quite a few years there were no other bars detected, despite the effort in putting follow-up of both this source and other regions of the sky. Nothing was coming up, and the community was starting thinking that this was just an interference, maybe some microwave oven near to the telescope, you never know. And indeed, there was a student that did a check and found that interferences could produce a similar bars than what you observe. Until 5 years later, when 5 more fast radio bars were discovered, also with Parkes. So this was starting to be something real. You can see in the plot where the Lorimer Parkes was, and it was really peculiar with respect to the other population of radio transit. So it was either something very new or something very wrong. So then in 2014, there was the first detection of fast radio bars, also in archival data, but this time with Arecibo telescope. It is not working anymore, but it is radio science. And since this was observed with a different telescope, it was also reassurance that it was a real phenomenon. it was not something local due to the park's electronic or something else. And this also allowed to verify that some of fast radio bars are repeating. Indeed, just a few years later, while Laura Spittler was monitoring this object, this region of the sky, it reactivated and produced 11 more bars. These bars were localized in the same region of the sky and with the same temperature measure. So despite Arecibo has not a very high resolution, she was able to match these bars with the previous discovered fast radio bar. So this was the first example of a repeating fast radio burst. It was really important because it allowed to do a follow-up with high resolution instrument like the VLA and locate the bars inside this host galaxy. So this opened new venues in the study of this phenomenon because it allows you to study the environment where they are present and what makes them peculiar. Also, for this kind of repeating fast radio bars, they were able to exclude the catastrophic nature of force because it's able to repeat itself. So it cannot be something that happens just once and then get destroyed. But what changed really the field was this telescope CHIME that started working in 2018. It's really a war machine that is able to locate fast radio bars in the entire sky above the telescope, 24 hours, 7 days. And it gave the opportunity to have a much bigger census of this phenomenon, these transients, and open new possibility for, in particular, for repeating fast radio bars, where you can then study also the environment and the host galaxies of this phenomenon. It is going through an upgrade, so with the addition of this external station that works as a BLBI telescope, it now allows for a localization sub-arcsecond precision. So you are really able to have an immediate position, an immediate localization of the host galaxy without doing a follow-up with other instruments. And this is just the period that these stations are starting to work, and I will show you some of the first results later. In the future, there will be much more instruments that will be able to unveil the mysteries of fast radio bars. There will be an expansion of a CHIME that will include also single dishes working as an interferometer. There will be also an enough instrument that is the upgrade of the Northern Cross telescope. That was the first radio telescope in Italy, an historical instrument that now can find a future with the new fundings and with this new field. And also in America, there will be also the SA 2000 in California. This is also a huge project that will be able to pinpoint fast radio bars at sub-arcsecond precision. So all of these instruments aim at having more sensitivity and more angular resolution to target the fast radio bars. Another important step after CHIME started to work was the identification of the first galactic fast radio bars. This was in 2020. A fast radio bars was for the first time linked to a magnetar, to a gamma ray repeater in our galaxy. It was observed by Agile and Integral, so we can be proud of this. And these are the bars seen in X-rays and other X-rays with these two satellites, and they were only 6 milliseconds away from the main radio bars. So this was a confirmation that fast radio bars can be originated by magnetars, at least this one. And we started looking also into different bands to understand what's going on. Meanwhile, different groups started to observe the point where the fast radio bars was observed, but in continuum. And indeed, two cases of a persistent radio emission was discovered. That is continuum emission that stays there even after the bars has gone. The first one was detected with the VLA. You can see here. Zoom with the VLBI allowed to identify a compact source of the particle scale. continuous source that was associated with the facility bars. A second case was this one, also a parsec scale. So people started to believe that these were produced by magnetar and must be also present a sort of bubble of plasma around that produces this continuum emission. So must be a persistent object in the sky. Meanwhile, more theories were coming up about the physical origin of facility bars. The two main models were one where the bars is produced by the magnetosphere of a magnetar, and this is most probable for the case where the association with a magnetar is valid. In another model, you can have a shock wave similar to the one that is linked to gamma ray bars, where the bars are produced by the shock, and then you can have also propagation in the medium that give origin to the persistent radio emission we were discussing. So it's not completely clear how it works, but we have more and more clues about how some facility bars are linked to magnetars. So let's see this. The case of these facility bars that was associated with a persistent radio source that we discovered in 2021. We started with a low resolution when Chime published the alert about this repeating facility bars that was reactivating after a few months of silence. There were several follow-ups by different research groups. A first one detected a persistent emission with a GMRT that works in the megahertz domain. And after that, we also detect a VLA counterpart in the gigahertz range. So unfortunately, VLA was not in a extended configuration. That is the one that allows you to have a higher resolution. So what we could do was to push the frequency up to 22 gigahertz and recover this emission that was all around the position of the facility bars. That is the yellow cross that you can see here. We could count on the parsec scale position of the facility bars from the precise collaboration. That is a collaboration involving different EVN single stations that is able to track the bars and gives the position on a parsec scale. So pointing to that, we could see this extended region of emission in the radio, and we could also locate the center of the host galaxy, that is the red cross. And we also performed some follow-up with the LBI instruments, both in Merlin and EVN, to check the presence of a compact persistent radio emission, but it was not there. So we were convinced that, of course, the fast radio bars line was embedded in a star-forming region that is already interesting because it allows you to link them with young magnetars, but we were not seeing directly the compact emission from the persistent radio source. So this was our first work. After this, some more colleagues performed the observation in different bands. This is an optical image with keck. You can see the host galaxy and the position of the fast radio bars here. So it was really in a position that was not special because it's not on the arm, it's not in a very dense environment. So we were puzzled by this result, but at least we could have a very nice image of the host and plan some further observations. Another group observed also with the VLA at a resolution that was slightly higher than ours and at 6 gigahertz, and they could also see not only the region that was where the facility bars was embedded, but also the bar of the host galaxy. So they were confirming that there was some obscured star-forming emission in this region, and this was reassuring because we could also see at higher resolution that the region was real and was coincident with the facility bars. Also, there was this little spot here that deserved further observation, and that's what we did. We observed a higher resolution, 15 gigahertz with VLA that meanwhile was moved in a more extended configuration, allowing you to zoom into the region. And we detected this spot of emission that is compact and is consistent with the position of the pulsar bars. This is the angular resolution of the DLA for these observations. So this compact emission was also giving us the information to track back what you see in this other image. So we performed a different image analysis of this region, and fitting a plateau of emission due to the star-forming region here and fitting a Gaussian on top of this spot here, we could disentangle the contribution of the compact emission linked with the pulsar bars for the more diffuse star-forming region. So we could build an SED, and we also complemented that with millimeter observation with NOEMA. These are very important because it allows you to put a constraint on the star-forming rate of that region. And we got an upper limit of 2 solar masses per year in the region of the pulsar bar. So while if you look at the entire host galaxy, you get less than 8 solar masses per year. So these both were non-detection with NOEMA 230 gigahertz, but we could at least set very constraining upper limits. When you superimpose the data that we collected in the radio, lower resolution one in blue, the highest resolution one in black, with the upper image of the host galaxy, you can see that the emission is very localized around the pulsar bars region and is distinguished from the center of the host, that is much southern. So we also did a follow-up in the optical band with GTC Megara, that is a IFU unit, allowing you to have a spectrum for every one of these pixels that you can see here. We imaged the entire host galaxy. You can see the bar here. And we could extract the spectra for the region of the pulsar bars. You can see what you can do with Megara is really wonderful. You can have a pixel in correspondence of the pulsar bars and extract the corresponding spectrum. So we detected the H alpha line. We could estimate in this way the star-forming rate in an independent way with respect to the millimeter band, and we obtained a star-forming rate that is just lower than 0.1 solar masses per year. So it is indeed an obscure star formation, but the radio counterpart that we detected, if you try to explain that with the star-forming activity, you need at least 3 solar masses per year. So both of these limits that we got from NOEMA and from Megara were not in agreement with the power that the star-forming rate that you need to produce the luminosity of the compact emission linked to the fast radio bars. So we were pretty sure that this is due to the fast radio bars itself and not to the star-forming region where it is embedded. Okay, we really need to put together different pieces of the puzzle to understand what's going on. So we were convinced that this was a continuum emission due to the fast radio bars. So we started to browse the models that try to explain this kind of emission. There are different models, but basically they are all about a sort of bubble of plasma that is inflated either by an X-ray binary wind, that is an hyper-accreting system, or simply a nebula all around the magnetar that has been inflated by the activity of the magnetar. So we try to put our object on the expected relation for the nebula linked to a magnetar, and we could expand the interval of the explored parameters by almost 2 orders of magnitude, because you can see here the previously discovered PRS that were at a higher rotation measure, that is an indicator of the magnetic field and electron density in the environment, direct environment of the pulsar bars, and the luminosity in the y-axis. So we could go down to lower luminosity and to lower rotation measure, and this falls nicely on the expected relation. So we were able to confirm that at least in these 3 cases, the continuum emission is consistent with the model of a nebula around the magnetar, further confirming the association of this kind of fast radio bars with the magnetar. What you can see here is the radio LCD of our object and the other two. What is most striking is that this is inverted with respect to the other two. So we were also puzzled by this. These are the NOEMA upper limits that you can see here in yellow. And we are pretty sure there should be a peak around a few tens gigahertz, and I show you some preliminary results from ALMA that shows you a data point here. But for the time being, we only support a power law, and all the possible ranges are consistent with errors. The NOEMA upper limit, nevertheless, already excludes some of these possible power laws. So there should be something here that goes down at high frequency. So this is the nice representation that an RAO artist did for the press release, and you can see here the nebula all around the magnetar, and this is basically the scheme of how the model works. The radiation from the nebula is produced by synchrotron emission, and the rotation measure is due to the density of the electrons and the magnetic fields in the nebula itself. So as I was mentioning before, this is still consistent with an hyperaccreting X-ray binaries, although we got very tight upper limit on the X-ray emission. So maybe at least for this case, the magnetar is powered, and indeed there were some works later that could explain the bars themselves with the processes that you expect in a magnetar environment, the magnetosphere. And this is a wider example of how it could work in X-ray binaries. You have a more extended region here that is inflated by the winds produced by the accretion of the compact objects. And all these areas through shocks should enlighten the continuum emission that we see. So we are still discussing about this, but we are happy that we could confirm the nebular origin of our fast radio bars. These are preliminary ALMA results with archival data. We applied for ALMA several times, but unfortunately we did not get the observation. But at least we could have a look at this archival data that just became public. And the goal of this data was to study the host galaxy, the CO emission from the host galaxy, but we could stack all the spectral window and produce a continuum image at 100 gigahertz. You can see that when you compare with the VLA image, the persistent emission from the fast radio bars goes down with respect to the core, the center of the host galaxy, and that's perfectly reasonable because you expect in the millimeter more contribution from dust that is more abundant in the center of the host, while the region where the fast radio bars is should go down in frequency. And indeed, these were not so high resolution observation because ALMA was in a compact configuration. So we can propose something better at the next data line and go to higher frequency, but still, if you feed these two with two Gaussian and you try to disentangle the contribution from the host center, you can measure a flux that is below the expected trend for all the possible power loads given by the previous three measurements. So this is a first indication of a peak that should be around here. And it will be at least consistent with a very compact and young nebula, okay? So let's see another case of fast radio bars that we just published. Also in this case, we were able to detect a nebula, but as I told you for the previous one, everything started at a lower frequency and resolution, of course. And indeed, the first indication of a possible continuum counterpart was with MERCAT and with the UGMRT. You can see the angular resolution of GMRT yellow and MERCAT red. So both these observations provided the first indication of a continuum emission, but since you are including the entire host galaxy inside this observation, you can be sure that the radio emission comes from a star-forming region or from the fast radio bars itself. So it was needed to go to higher resolution with VLBI, and that's what we did. We proposed with the VLBA at 5 gigahertz, zooming it into the parsec scale. You can see the beam scale is about 4 parsec. And we could spot this compact emission. That was the only statistically significant peak in the entire localization region provided by the precise collaboration that I was mentioning before, that was able to localize the fast radio bars just slightly south of this position. So this was a 5 gigahertz measurement that allowed us to put a point here. These other two are GMRT and Metcalf. At different scales, of course, so you have to be careful when you mix them to build an SED. But there was already a first indication of a possible peak, and that's what another group confirmed through higher resolution VLA observation. So this first indication turns out to be true. We also, in this way, we have another case of peaked PRS. That is an intermediate case between the first two ones that are quite steep, the inverted one that we discovered 1 year ago, and this one that is intermediate. It has a peak, but is at lower frequency with respect to the green one. And so it allows us to study better how this nebula works and constrain their model. So now we have another point here, and it is at the boundary of the expected relation. The two lines that you see here are given by the constant that you shoot here that depends on the environment. So you can still stay in a safe region and include all the 4 PRS discovered so far. Plus, we have 2 candidates from a work that was published last year. This is also a lower resolution work with the VLA, so we are going to observe them in a month with the EVM. We are going to confirm or not the compact emission from these 2 candidates. This would be very nice because it allows you to go even at lower rotation member, lower luminosity, expanding again the range of the nebula properties that we are building. The host of these fast radio bars turn out to be also a small but star-forming galaxy. So also the link between fast radio bars and star-forming galaxies seem to be strengthened. Despite there are also exceptions. You can find fast radio bars also in hosts that are not so active from a star-forming point of view. We are still building the puzzle. So Chime keep discovering repeating fast radio bars. Now we have 60 repeating fast radio bars, and we could target each of them in principle to discover nebulae associated with them. And meanwhile, there were also some work that suggested a link between repeating and non-repeating fast radio bars, meaning that in some cases, when you see a single fast radio bars, it could be a fainter fast radio bars that is repeating, but you can see only the brightest bars, okay? So you only see the tip of the iceberg, but there are many more bars at a lower luminosity. So also the community is still discussing whether these are 2 different classes. Somebody proposed that no repeating fast radio bars are linked with catastrophic event, just like a neutron star mergers, while repeating fast radio bars should be magnetars. We are still trying to understand this. So we have discovered 4 PRS. We are building a better model. We have 3 more candidates, and many more will come with future facilities. But also, the universe is really merciless and keeps destroying our weekends. So just 2 weeks ago, we got this alert from Chime about repeating fast radio bars. And this time it was really important because it was nearby. It was the most nearby after the Galactic one, the Galactic magnetar in 2020. Indeed, it was located in NGC 4141. That is only 40 megaparsec away. You can see the host here. The position of the fast radio bars is the Cian ellipse here. this was also, I think, the first time China could use the data from the outrigger station, so the BLBI station, to localize in a better way the fast radio bars, but it was the most nearby one, so you can still have a long beam of one axis and a short one in the other direction. This already allow us to perform some follow-up. Einstein probe detected a candidate X-ray counterpart, so we observed with the Merlin, and we could be able to exclude the presence of a persistent radio emission with the Merlin at 5 gigahertz down to a luminosity of 10 to the 26. This is already, thanks to the distance, the short distance of NGC 4141, this is already 2 orders of magnitudes lower than what you have for the other nebulae. So we are quite confident that a nebula is unlikely. Indeed, this is a non-repeating fast radio bars so far, because you never know. This is a nice image showing you the new localization of Chime, including all the outrigger stations in North America. So you can see the huge difference between the green ellipse, it is the first localization, and the improved localization when they could process data from all the stations. This is a super-second localization with an error of 150 milliseconds. So this is striking and allow us to do a much better work matching the resolution of the RBI facility. So unfortunately, the X-ray counterpart by Einstein probe was discounted by deeper channel observation, but still we are following these fast radio bars also with BLA possibly. We sent a DDT and we are still waiting for the reply. And this could be important because of it, of course. So what we will do in the future, we want to expand this sense of nebulae. We want to understand whether repeating and non-repeating fast radio bars are linked, if they are different populations, why the nebula is present in some cases and not in others. We need to consider that these observations are done at the limit of the current facilities because you need both resolution and sensitivity in the radio. So we are pushing the capabilities of modern arrays. And in the future, thanks to SKA, VLBI SKA, that will be also important to reach the resolution we need, and next generation VLA, we will be able to expand this population of counterparts to lower luminosity. Let me mention also some of the other activities we are doing here in IAPS, not only fast radio bars, but as you know, we are working also on gamma ray bars with different research lines. There are high-redshift gamma ray bars led by Aish, X-ray flashes by Julia, and of course the GW follow-up that somebody knows if we will be able ever to see something else, but let's try. And it will go on until next autumn, so there is still time. So at the moment, we are following fast radio bars. We have an active fast radio bars, an active high-redshift GRB, and an active X-ray flash. So we are all busy with these new kind of transits. We also take advantage of Einstein probe collaboration. And for the AGN nuclear transits or reactivation, we can count on CRISP and XP for at least 2 options. Far, we have NGC 4051, which we are following with Einstein probe, and NGC 7213 that just reactivated a couple of years ago, producing high luminosity in the X-ray, and we are following that to see whether or not the jet will be produced. So there are many activities involving different instruments. I'm glad to lead the radio part, and I think this can give a very good contribution to the study of the non-thermal emission from these different kind of transits. The last spot, if you want to know more about fast radio bars, there will be the first national workshop on fast radio bars in Bologna in May. So you are all invited, and I hope this new field will raise interest in the community. Thank you very much.
Very interesting talk about this important topic. You have questions or comments? Yeah.
I just have a couple of curiosities. Was there any attempt to detect the passage burst during the burst fast optical instruments, the new ones?
They are trying. There are
What
different.
do you expect?
Yeah, sure.
Optical line, so optical flux.
Yeah, there are projects studying F2 that should be blue transients in the optical, and they try to limit that with passive bars. But so far, I think there was no detection about that. But the community is really using everything
So
possible.
there are upper limits during the bursts.
I think, at least for some objects, there should be something. Yes.
If I may add something to this, actually there are very tight upper limits on X-ray counterpart of fast radio bursts, including the one that you have presented. Actually, during that observations, we had a Chandra campaign going on, and there was a sequence of fast radio bursts that coupled by actually the Sardina radio telescope, and at least 100 bursts by FAST, the Chinese telescope. And on the top of that, we had the Chandra observing, and unfortunately, we couldn't find any simultaneous photons. Actually, we did get the Chandra detection overall of two observations, but we believe that is due to the star forming region. So no X-ray, gamma ray counterparts.
So this upper limit would be consistent with the synchronous interpolation.
Yes.
Yeah, and this was at redshift 0.1. So it is really important to follow up the galactic fast radio bars and the nearby one, like the one here in NGC 4141, because it can give you more height constraints, multi-wavelength emission.
The second main question is whether there are upper limits on periodicities in the radio.
Well, it can be different. Yeah, you can have, for example, repeating fast radio bars can have a bunch of a single bars at the beginning, then a bunch of bars in a few days, and then they stop for a month. And
I'm talking about the persistent counterpart.
For the persistent, okay. Yes, there are upper limits for some of the repeating ones. You can see in the plot here. All of these blue ones are upper limit on the radio luminosities. But what is important is to stay on the right side of this plot, because below this, the rotation measure can be due to the host. So you cannot disentangle really the rotation measure of the fast radio bars from the host. So people just keep following these repeating ones and putting upper limits here, but it's important to stay on this side. And on this side, we could detect almost all of them, except this one. So this is what you were meaning for. Okay.
Maybe connected to this point here, there is also, maybe you didn't mention that if these bubbles are really, what we believe connected to the burst, we should possibly see some hint of variability on the time scale of years. Actually, one of the goals of the program is to monitor the persistent radio source throughout time to see some. On a couple of these, there was some suggestion of long-term variability.
The yellow one here is showing a variability in the luminosity along months. So there should be an evolution of this nebula, not only a static bubble. Yeah.
Questions? Just a curiosity, exactly on this slide, if there is any correlation between the slope of the curves and the luminosity. Not flux.
Well, these two are more luminous. This is the lowest. Let me check. No trend, no clear trend. But if you look here, yes, okay, this is the most faint one, and it is inverted. So the self-absorption can cut your luminosity. You mean luminosity in the radio, or? Okay. So this is intermediate, and these are more bright. So it depends really on the shape of the spectrum, because if you get self-absorption, then luminosity goes down.
Questions? have a curiosity on this one. I'm not an expert on this field, but regarding high energy counterpart of this, actually we detected
Sure.
an energy counterpart of one of the events you report here, super agile instrument, and we published other paper on the upper limit. One is impressed by Claudio Casentini. And in your opinion, according to your experience, we have chance to detect an high energy counterpart in EV or GB.
You mean the bars? I'm not really expert on the bars itself, but maybe for the most nearby one, yeah, I will make an effort to.
Is there any model
Not yet. Magnetar magnetospheres are the most probable one. So maybe you can extract some expected flux from there, fluence. Yeah.
Thank you. Okay. No questions from the Zoom audience. If we have no more questions, we can thank the speaker again.